This is lab for bar magnets. So the purpose of this lab studied distance dependence of the magnetic field of a bar magnet and the op-axis magnetic field of a magnetic dipole. So to do this, we'll just be using the fact that it's a dipole and the Biot-Savart law. And it was found that we almost closely match the expected relationship of 1 over r cubed, but we got like 1 over r to the 3.64, something like that. And the magnetic dipole moment of the bar magnet was 6.78. It behaved like a magnetic dipole. So these are the equations that we use. We assumed that the magnitude of the bar magnet was in the form kr to the n, where n was a constant to be found. And so as an extension, we have this expression in terms of logarithms. And then check our answer, we use the fact that the magnetic field of a dipole can be modeled by this equation right there. And lastly, and this one right here as well. The reason we can do this is because we can treat the bar magnet as a magnetic dipole, especially from far away, and their assumptions are that the magnetic field is only the one of the bar magnet and the Earth, and that the observation distance is sufficiently large. So for the first experiment, the system is the bar magnet and the phone surrounding is the Earth, and we just have to keep into account the B field of the Earth in Atlanta. So to do this, we just aligned the magnetometer at different distances from the magnet to determine the relationship between distance and the strength of the B field, and then we linearize the data to find the value of n, and then also use that to find the dipole moment of the bar magnet.
Here's a photo of the experimental setup.
So here are results when we graphed the data and linearized it by taking the logarithm. We found that our value for n was negative 3.64. We're expected negative 3, so it's pretty decent results. And that our y-intercept, which is ln of k, resulted in the value of the magnetic dipole moment of the magnet to be 6.78. So for this experiment, we also used the bar magnet in the phone. The surroundings were also the Earth, and the point of this was we aligned the phone at the 45-degree angle off axis and measured the magnetic field at this location, and compared those to the following computational model. The results from this is that we found these are our numbers for the off-axis field. They're represented here below. They don't really have much meaning until we compare them with the code. And it's true that the magnetometer is far away from the magnet, measures a near zero magnetic field in the x direction because the inverse relationship. It's false that the decrease as we move closer actually increases, as we have here. Um, yeah. So for our code, we tried to model the same situation. So to do that, I first created a function for the B field based off the magnetic dipole moment and the radius, which we have here, or the observation vector, essentially, using that equation from before. And then we plugged in our initial values that we got from the experiment. So 6.78 for the magnetic dipole moment, and this was the distance that we used for the second part. Um, yeah. So then using that, we modeled the B field at 6 different locations, 2 parallel and then 4 perpendicular to the magnet. And so these are results. Keep in mind that this one and there's also one behind it are the ones that are in the z-axis perpendicular to the bar magnet. But this is consistent with our expectation for what the magnetic field of a magnetic dipole looks like at a sufficient distance away. Like same thing as a dipole. Yeah, so similarities is that the B field op axis depend on both the x and y distances for both the experiment and the code. The magnitude of the B field increases as you get closer to the bar magnet, but we did see some differences in the B field, but the order of magnitude is consistent with our expectations. And our key assumptions are the same as before, that the magnetic fields are only those at the bar magnet of the Earth, and the observation is sufficiently larger than the length and width of the magnet. So these are the values that we got from our code and for experiment. You can see there's a very slight difference in the numbers, but the order of magnitude is the same. And so the reason is likely because maybe the magnetometer on the phone isn't entirely accurate, wasn't perfectly aligned, and that there's other magnetic B fields from other electronics or other magnets in the room that interfered with our measurements, as well as some just basic human error collecting the experimental B field. So if we hadn't oriented it, then we would have had like some other, like the Earth axis, the Earth's magnetic field would have contributed to the on-axis magnetic field, which is like the one that we measured for X. So in measure results, because it's relatively constant for small changes in position, this like added constant would be the same for all the positions around the magnet. If we had two identical magnets, we would essentially just expect a doubling in every numbers because of the superposition of B fields. Again, assuming that we're a sufficient distance far away from the magnets. And that's also because the B field of the bar magnet is independent of the B field of its surroundings. There's just like caveat, but this is the case for the most part. So, in conclusion, we found the relationship did closely match our expected 1 over r cubed. We got 1 over r to the 3.64. The distance dependent can be used to calculate the magnetic dipole moment of a bar magnet, which we found to be 6.78 in this experiment, and that the B field of a bar magnet is like that of a magnetic dipole, both on and off axis. Thank you.